Okay, nice. So therefore, in this paper, we would like to design a model agnostic and demographic agnostic fair recommendation method, and we call our method agnostic fair SIGIR, abbreviated as AFSR. So there are basically two design principles of our method. The first one is model agnostic, which means that we require our method to be it should be readily employed for arbitrary sequential recommenders like Bert-Forek, SESREC, or NUM. And the second design principle is demographic agnostic. In this case, we require our method shall achieve group fairness without using users' demographic information at all. Okay, before we dive into the technical details of our method, I would like to firstly present a key hypothesis of our method, which we call demographic stereotypical patterns. So imagine we have a male user who is browsing some items for some important events, and in his browse history, there are some cosmetic-related products. And if we assume the recommender is biased, then it is prone to focus on making recommendations on the stereotypical patterns and therefore return some stereotypical recommendations. So we hypothesize that such stereotypical patterns are just some superficial features and are associated with shortcut learning during model training. And in that case, this kind of stereotypical pattern may trigger a large training penalty. And indeed, to validate our hypothesis, we firstly performed some pilot study where we report the recommendation performance and DCGS3 and the training loss, as well as the norm of the training gradients with respect to the item embeddings. So we can see in this example on the movie length 100K, we see the underrepresented minority group is female group because the recommendation performance is actually lower on this demographic group. And correspondingly, the training gradient norm is actually very large on this female group as well. Therefore, we will be leveraging this key information to develop our method. Okay, nice. So our method consists of two modules. The first module is Dirichlet neighbor smoothing. So the first step of this module is to actually estimate stereotypical patterns via training gradients with respect to input embeddings. So for instance, assuming we are given a user sequence from X1 to XL, where L denotes the length of the sequence, and we firstly embed all the discrete item IDs into continuous representations using our embedding layers, and then we just directly locate the item with largest gradient and treat this item as the most stereotypical item within user's history. And centered at the located most stereotypical item, we just expand the span of size 2s+1, and we say this is our located stereotypical embeddings. Of course, we can also map this embeddings back to the item space, and we can recover the located stereotypical pattern. So with the located stereotypical pattern, then the second step of our method of this module is to compute the smoothed items with k-hop items with Dirichlet weights. So for each item within the located stereotypical pattern, we firstly compute the k-hop neighbors using similarity, and this demonstrates as a span over the item space, the embedding space. And we can see some neighbors are similar to the original item, and some other items are actually very far away from it. So, and then we will sample some random weights from the Dirichlet distribution, and then we compute the weighted sum of the neighboring items to compute the replacement item embedding for the original item. So in this way, we are essentially introducing some randomness and new items into the raw user history, and such a design could effectively reduce the correlation between the stereotypical patterns and the final recommendation results. So essentially, we are transforming the original user item embedding into a smoothed item embedding here. So in addition to Dirichlet neighbor smoothing, we also our method also adopts worst-case performance optimization. So the key intuition here is that, recall, I just say we performed a pilot study validating that larger gradients, training gradients may be triggered on the minority group. Therefore, it is possible for us to estimate the underrepresented group, in this case using the gradient information, even if we don't have the actual user demographic labels. So, but of course, it is clear that there is a gap between the real underrepresented group and our estimated one. Therefore, we would like to adopt distributionally robust optimization to achieve better generalization, overcoming this gap between the estimated one and the real one. So essentially, the first step is to estimate the underrepresented group with large gradients. So in that case, we will just compute the estimated demographic label for each user who with using their largest training gradients. As we can see, we are still computing the training gradients with respect to the input embeddings and set the max value as the demographic label. But this is not the true demographic label. So, and then we will merge the users with top K largest gradients together, and then we say we are forming them together to a set of underrepresented users. And in that case, we will be optimizing the DRO loss over the estimated underrepresented group, like I highlight here. So the DRO loss essentially is the weighted sum of the individual training loss over the smoothed item embeddings, which I introduced in the Dirichlet neighbor smoothing module. So the overall framework of our agnostic fair SIGIR looks like this. So we have the Dirichlet, we have a Dirichlet neighbor smoothing module, and then we generate some smoothed sequences, and then we use the gradients to estimate some underrepresented group, and then we employ DRO to overcome the gap between the real underrepresented group and our estimated underrepresented group, so that we can maintain the performance improvements on the minority group, and essentially we are able to achieve model fairness. So when training the model, we are optimizing a combination of two losses together, as I show here. So the first loss is a very classic ranking loss, which we use for training arbitrary recommenders. And the second one is the DRO loss I just presented. And we also introduce a non-negative factor lambda here to trade off these two terms. Okay, in terms of experiments, we adopt movie length and last FM to evaluate our method, and we process the dataset with 5 core, and we use gender as our sensitive attribute. Note that we only use this gender attribute to perform evaluation instead of model training, and in terms of fairness metrics, we adopt the performance gap based on recall and NDCG across different demographic groups. And we also evaluate our method on different model architectures to validate it is indeed model agnostic. So we test it on BERT4rec, SASRec, and NUM. So the first group of results are about fairness evaluation. So we evaluate our method on different datasets and different model architectures, and we also compare our method against different baselines. So from the table, we can see our method can indeed achieve better model fairness, even if we do not have access to the label, the demographic label of the users. And I want to say the baseline is actually some like regularizer or importance reweighting or adversarial debiasing. They actually require the user demographic information. So we have to assign some user gender label to the baseline method to make them work. Okay, and in addition to fairness, I also report the performance here because we want to make sure our method is actually not a trivial fairness method. So we can see our method can actually achieve comparable comparable overall recommendation performance here. And we also perform an ablation study where we randomly masking out either module of our method, namely the Dirichlet neighbor smoothing or the DRO loss. And we can see removing either module leads to worse fairness, so which also in return validates the importance of these two modules. property of our method, which we call universal fairness. Because during training, we do not require our method to use specific demographic label or sensitive attributes. So we expect our method can automatically achieve universal fairness with respect to different attributes. So if we directly use the model to test on the different demographic attributes, for instance, in this table, we are grouping users using their job, occupations, and then we still evaluate the performance gap between the different occupation groups, and then we can see our method can actually perform better than the naive trained biased model. So this is a very nice property, even if we do not care about which arbitrary demographic attribute we are talking about. So I actually think this concludes my presentation, and I would like to thank you for your attention. If you have any comments or questions, please feel free to reach out.